Okay, good morning, guys. Today's, I don't know what section we're still in, 4.6, day 3, hardest of them all, cones. And we're going to start out, we're going to do two cone problems, and then a shadow problem. I never liked the shadow problem either. But sand falls from a conveyor belt at a rate of 10 cubic meters per minute onto the top of a conical pile. Okay? Conical pile, what does that mean? Well, a conical pile is and I got my little conveyor belt coming up. A little wheel there, comes down, a wheel there, and the stuff is coming up and it's dropping on top of the pile. Okay, conical pile is basically, it's just a cone. And what makes these hard is I have a radius and I have a height. And if you notice there, the volume of a cone is 1/3 pi r squared h. And what makes a cone hard is as your cone is growing, the radius and height, they are both changing at the same time. Okay? So contrary to a cylinder, my radius was constant, but in a cone, the bigger my conical pile gets, the bigger the radius, the taller the height, and so I have two changing values here. Okay? So sand is falling from a conveyor belt at a rate of 10 cubic meters per minute. So that kind of tells me dV dt equals 10 meters cubed per minute onto the top of a conical pile. The height, this is a special relationship in a cone, the height is always 3/8 of the diameter of the base. So I know my height equals 3/8 of the diameter. Now, this is going to change for all cones. It's not the same thing for all cones, but in this particular cone, for this particular grade of sand, the height is always 3/8 of the diameter. And what they want us to do is how fast, find that rate of the height first, and then the radius changing. So they want me to find first in part A is find, okay, dH dt. And they want me to find that when my height is 4 meters. And then there's a little extra thing here. They want their answer in centimeters cubed per minute. And sometimes they will do that on you. They're going to make you change units in the end. It doesn't matter if you do it before or if you do it after. But we have to make a conversion. And h equals 4 meters, not h 4m. Okay, so as I go here, the relationship, like I said, in a cone. Okay, no matter where my radius is and my height is, if you notice, these are always going to be similar right triangles in there, which means I can make a proportion of radius to height. And they're always going to give me a little something in here, okay? And what I want to do is I know I need to find dH dt here. That's what they want me to find in part A. Given h is 4, dV dt is 10 cubic meters per minute, and the height equals 3/8 of the diameter. Well, what I don't want to do here right away, because I can see here in part B, they also want me to find, okay, dr dt. And if I came here right away, which we're not going to do, if I took my derivative with respect to time, okay, number one, I got a product in here. The product isn't the big deal. But if I took this derivative, dV dt is going to equal, I'm going to put these two here together quick, as pi over 3, and then I'm going to differentiate my product there, which is going to be 2r times dr dt times the second term h, plus the derivative of the second term, which is going to be a dH dt, times the first term, which is r squared, And if I look at this equation is really unusable for me because these are the two things they want me to find in the equation. So, okay, I need to know the radius, the height, the radius squared. So if I know the radius and the height, I'm going to have to know both dr dt. I'm going to have to know one of those to solve for the other. I do know dv dt, but the reason, because I'm going to have two unknowns in the same equation, I'd probably be able to do it in the end, I'll be honest. However, I don't want to make it hard. So I'm going to come back and I'm not going to find the derivative right away. I'm going to use some of my relationship between my height and my radius so that I might be able to rewrite my volume here a little bit. Okay, so bottom line, I know the volume of my cone is 1/3 pi r squared h. Now, I also know that h equals 3/8 of the diameter. Well, that's great. I need to know the radius. Well, okay, I do know, if I think about this, I do know the diameter. The diameter is technically 2 radii, so I know my height actually equals 3/4 of the radius because I can reduce those, okay? And in the end, what they want me to find first, technically, is they want me to find dh dt. Okay, and if they want me to find dh dt, that means I need to get rid of my r in here. So wouldn't I be able to also say the radius actually equals 4/3 of the height? So that I could substitute that in for my radius, and then I have my whole volume function in terms of height. And then when I differentiate it, life is going to be good. So let's take a gander at that. The volume is going to equal, well, I'm going to take this, I'm going to call that pi over 3. Now r is 4/3 h squared times h. So my volume function really is going to equal, well, that's really going to be 16/9 when I square it, right? So I'm really going to get 16 pi over 27 times h cubed when I simplify that guy out, right? Because 4/3 squared gives me 16/9. My 16/9 times my pi over 3, that's where my 16 pi over 27 comes from. H squared times h gives me h cubed. So now I'm going to take the derivative of this guy with respect to time, okay? So as I did that, and I'm going to need a little bit more room here, but as I do this, well, now I know dv dt is going to equal 16 pi over 27 times 3h squared. And I wanted to write that so you could see these two guys, they're going to reduce. So dv dt really is going to equal 16 pi over 9 h squared. Don't forget your chain rule, Kruger. Dh dt, so times dh dt. Well, the beautiful thing is I know dv dt, I know what h is, so I will be able to solve for dh dt. But remember, in the end, I need my answer in centimeters per minute, and everything I have written right now is in meters, okay? So for meters, dh dt is cubic meters per minute. And I could do the conversion of 10 cubic meters. Most people are going to screw that up. It's actually 1,000,000 cubic centimeters per minute. So I think it's going to be easier to do our conversion at the end. So I'm going to plug in here. I'm going to plug and chug. Hopefully we know dh dt. Hopefully we know our units are going to be, in the end, centimeters per minute, because the height is a linear unit of measure. And I'm going to plug this in, dv dt. The pile's growing at 10 meters per minute, and then that's 16 pi over 9 times, that's going to be 4 squared, times dh dt. Well, that's really going to be 10 equals, well, 4 squared is 16 times 16 is 256 pi over 9 times dH dt. And when I solve for dH dt, what I'm actually going to do is, hopefully you know that, we're going to multiply both sides by 9 over 256 pi. So times 9 over 256 pi. And we're going to find out dH dt, as the 9's cancel, that all cancels, it's going to equal 90 over 256 pi. And now this is meters per, is it meters or per second? I think it's per minute, meters per minute, okay? Okay, so now what I'm going to do, that's a pretty gross unit of measure. So all I'm going to do is I'm going to find out what is 90 divided by 256, and I'm going to convert that into a decimal quick. Now, make sure when you're doing this, guys, I hope you really use your control divide. So you're taking 90, it's working on me again. So it's really 90 over 256 times pi, and that is going to equal 0.11906, okay? So 0.11906. So 0.111, I already forgot, 906. 906, but that's meters per minute. That's what my dH dt is. So to convert meters to centimeters, we just take it times 100, right? So I should have 11.191 centimeters per minute should be my change in height with respect to time, okay? Well, there's one. I just found dH dt. Now, they want me to find dr dt. Okay, well, I can do that. And notice, I don't have to come back here, really. You know, I could come back to my volume equation, and I could replace that with h and differentiate with respect to r. They didn't give me r, but I could plug my h into my r function here, and I could find it. I don't want to do that, because I already have a really nice equation that is relating my height and my diameter, or I already have a really nice equation relating my height and my radius at all times here. So what I'm going to do is I'm going to take this other equation here, okay, and I'm going to take my h equals, oh crumb, what was it? H equals 3/4 r, or I could probably take, because I'm already going to know dH dt, it doesn't matter which one I take, I should probably take the one that's solved for radius, because then dr dt is already going to be isolated. So that's what I'm going to do. I'm not going to use that one, and I'm going to come back here, and I'm going to say 4/3 of the height equals the radius. Well, that's the same at every instantaneous moment in time for this bugger. So I'm going to take the derivative of this guy with respect to time, and that's going to give me 4/3 times derivative of h is 1 dH dt, and that's going to equal derivative of r, well, that's just dr dt. So what I'm going to do is I'm just going to come back here, and I'm going to say dr dt equals 4/3 times my dH dt, which I already know is 11.191 centimeters. So I'm going to say 11.191 centimeters per minute. So dr dt actually is going to equal, so I already have this decimal locked and loaded in my calculator. Even if I go times 100, okay, 100. So there's my 11.901. So I'm going to take my 11.191, and I'm going to take that times my 4/3 that I have to, and that's going to give me 14.921. Okay? Oh, 14.921 centimeters per minute is my change in radius at that particular moment in time. What's my moment in time? My moment in time is when the height is 4 meters. Okay? I don't have to go through the whole volume differentiation all the time because I actually will always be able to use this linear relationship between radius and height or radius and diameter. There is always going to be a constant ratio between the radius and the height of a cone. Okay? That is always going to be there, and I'm going to be able to find that relationship using similar triangles. Okay? Big is too little. And I'm going to use my geometric relationship for that to find that. Okay? So now we're going to move on to number 7. Okay? Volume of the fluid of a cone is draining at a rate. So it's draining. Okay? So I know dV dt for my, I'm going to put cone down here, actually equals negative 10 inches cubed per minute. Okay? And they want to know, what they want to know is how fast, find the rate. How fast is the level? The level is the height in the pot rising when the fluid in the cone is 5 inches deep. So find dH dt when I know the cone, the height of my cone when cone is 5 inches deep. Okay, so why don't you process that for a minute here now. Okay, so hopefully you thought about that a little bit, and because they're giving us a volume here, all right, we have volume. The volume of a cone, what is the volume of a cone? It's 1/3 pi r squared h. In my pot is a little cylinder. The volume of my pot is pi r squared h. But remember, my pot is a cylinder. And what is the radius of my cylinder? This radius is always going to be 3 here, isn't it, in my cylinder? My radius doesn't change on the pot, but my radius will change in my cone. So I know the volume of my pot is actually going to be 9 pi times h. Well, what is the fluid? Do I need to know the radius in my cone? Do I need to know the radius in my cup? No. So how fast is the level in the pot rising? I can take my volume equals 9 pi times h, and I can take the derivative of this rat with respect to t, and I'm going to get dV dt equals 9 pi times dH dt. Okay? And that's what I'm trying to find. I'm trying to solve for my dH dt. Well, that's all well and good, guys, but I still need to know dV dt of the pot, and they didn't tell me that. All they told me was dV dt for the cone, okay? For the cone, well, it's leaking out of the cone at negative 10 cubic inches per minute. Well, heck, doesn't that mean dV dt for the pot, because it's draining out of the cone and it's going into the pot, doesn't that mean the pot is filling at 10 cubic inches per minute? But because it's filling up, that's a positive one? Oh, that is a crafty, those dirty little dogs. Okay? So then I do have everything I need, because here's my dV dt of the pot, and that's all I need to solve this guy. And I'm going to get these out of here for a second. So I know dV dt was what, 10? I think it was 10. 10 equals 9 pi times dH dt. So dH dt actually is going to be 10 over 9 pi, and it's inches per minute. Inches per minute. And If I really wanted a decimal for that, I could find a decimal for that. All I got to do is come. Please make sure you use your fancy control divide, that you're actually taking 10 over 9 pi, and you're coming up with 0.354, okay? So dH dt for the pot equals 0.354 inches per minute. Okay? So I didn't even need to know some of that other stuff. Now, they're saying how fast is the level in the cone falling at this moment? Okay, well, here we go. And what I'm going to do is I'm going to pause and I'm going to copy my diagram down here again. Okay, so I copied my sweet little cone, my little coffee making machine down here, and they want to know how fast. How fast is the level or the height? So they want us to find dH dt of the cone when dV dt is still negative 10 cubic inches per minute. And don't forget the moment in time up here was when the fluid in the cone is 5 inches deep. So that's when dV dt is at, and h equals 5 inches. Okay, well, that's where we're going to come. So we need to think about this. The volume equals 1/3 pi r squared h. And again, to find dH dt in the cone, okay, notice if I took the derivative of this right away, I do have a product right here, and then I'm going to have a dr dt and a dH dt with chain rule, okay? And please understand, the dH dt of the cylinder is going to be different than the dH dt in the cone, because my radius and height are changing at different rates than the height is changing in my cylinder or my coffee pot on the bottom. But if I look at this, because this is a cone, okay, what I'm going to do is I'm going to break it apart, and I know, okay, so here is the radius. The radius of my cone is 3 inches, and the height of I really shouldn't call it a cone because the top is cut off, so it's more of like a fulcrum or something like that. It's more of a funnel, and I know the height is going to be 6. Okay, but there are, okay, if I break this apart, if I'm looking in here, okay, here's part of my cone, here's my radius of 3, here's my height of 6. But as things change, my radius changes, okay, so here is a radius and then here is a height. So I have similar right triangles. And I don't know how you guys used to do it when you were in geometry, but I always did my ratios of big to small. So what I'm going to do is I'm going to take this guy right here, and I'm going to come over here on the side, and I'm going to make a ratio. Ooh, my height wasn't 6. Hold on, back up the train. This little guy right here for the pink, my pink or my fuchsia was 6, and the red was the height, right? So I'm going to think of big triangle to little triangle, and I'm going to say how I always did it was I said radius of the big to radius of the small equals height of the big to the height of the small. And I could set up a proportion because they're similar. And then that tells me 6r equals 3h. Okay, now what do I want to find? I want to find, my goal is to find dH dt. So that means I want h left in my equation, which means I want to replace r, I do believe. Okay, so I'm going to solve this equation for r. So r equals 3h over 6, or r equals 1/2 of h. Well, that's kind of sweet, because this relationship is true at every point in this funnel. So that allows me to rename my volume equals, I'm going to call that pi over 3 again. And then I'm going to plug in for my r 1/2 h. I need to square that all and take it times h. So volume equals, well, 1/2 squared is a fourth times a third. That's going to give me pi over 12 h squared times h cubed. Okay? Now when I take my derivative of this guy, derivative with respect to time, now I am cooking with coffee. So I'm going to say dv dt equals, 3, what's 3 times pi over 12? That's going to be 3 pi over 12, which is going to give me pi over 4 h squared times dh dt. And the moment in time is when h is 5 and dv dt is negative 10, right? Negative 10 cubic inches per minute. So I'm going to come down and I'm going to plug that in. And I'm going to say negative 10 cubic inches per minute equals pi over 4 times 5 squared times dh dt, which really gives me 25 pi over 4 times dh dt. That equals negative 10. And what I'm going to do is I'm going to multiply both sides by 4 over 25 pi times 4 over 25 pi. I can see this 25 and the 10 are both going to reduce by 5, so I can say that's a 5, and I can say that's now going to be a negative 2. So I really can say dh dt equals negative 8 over 5 pi, if I did my math right, I think. And if I really wanted a decimal for that, well, then I'm going to come here and I'm going to get that fancy little control divide in there. And I'm going to say, what the heck is negative 8 over 5? And I'm just going to write, did you know I won't do it, times pi. And I'm going to say enters negative 0.509. So dh dt equals negative 0.509 inches per second. And that is how my height is changing at that moment in time. Right up here when the height is 5, the height is changing at a little over a half an inch per second as it's draining out. Okay? So then, from there, we're going to go to the very last problem, which is our shadow problem. I don't like the shadow problems, but they're there. A 6-foot man walks at a constant rate of 5 feet per second toward a street light that is 16 feet above the ground. So, we got this nice little street lamp, and it's shining out and around. And I got a dude here. Put a body, give him a long neck, some arms. He's walking on the ground, except he's walking towards the light. And obviously, because it's dark, this is going to cast a shadow here. So here's my shadow, right? And as he moves toward the light, this angle theta up here changes the length of the shadow now, doesn't it? So a 6-foot man, this dude is 6 feet tall, and this is a 16-foot street light. And the man is walking, he's walking this way at 5 feet per second. Now I have 2 changing distances here now, right? And the street light's in perpendicular. Okay? So I have 2 changing distances. I have the distance between the man and the light pole, and I also have the length of my shadow right there that's changing. And those are the only 2. Well, my hypotenuse is changing, but that really doesn't have much to do with the shadow, okay? So what they want us to do, at what rate is the length of the shadow? So that means the way I have this written, dl dt, they want me to find dl dt when shadow is decreasing, so it should be negative, and the tip of the shadow moving is a different one when he's 10 feet from the base. So when x equals 10 feet from the base of the light pole, right? Okay, well, now I need to see here what's going on. Well, I do have a right triangle here, but I don't have a Pythagorean theorem. But what I do have is I have a similar right triangle to the dude, to the tip of the shadow, and I have another triangle utilizing the light pole all the way out to the tip of the shadow and coming back, okay? So in order for me to relate x in L, I got to think again of an equation. Well, the way I think of these, I think of the light. This side of this triangle is to this side of this triangle. So I think of 16 is to 6 as the big side of the triangle, which is going to be x plus L, is to L, and I have an equation that relates these two. And I also know this 5 feet per second, is dx dt, because this is the man walking towards it. Okay, so that's, and dx dt equals 5 feet per second. Okay, so how is the length of the shadow? Because the length of the shadow is going to be L. Well, I have a nice equation, might not be nice, but I have a proportion relating these two, which is going to allow me to say 16L equals 6x plus 6L. If I cross multiply, right, I'm like, ooh, I got some like terms here. So I could say 10L actually equals 6x. So I'm relating x and L. I can get them on the same side, equal to 0. I can do whatever I want to do. But I know in the end, I'm going to have to solve for dl dt. So I'm just going to leave my dl and my dx. I'm going to leave them on opposite sides. But also notice, this appears to be more of a linear relationship now, doesn't it? So here, this is relating them. So what I'm going to do is I'm going to come here, and I'm going to take my derivative of my cross products of my proportion, and I'm going to say the derivative of 10L, well, that's 10 times dl dt. That's going to equal derivative of 6x, that's going to be 6 times dx dt. And what are we solving for? We want to solve for dl dt. Well, do we know dx dt? Heck yeah, we do know dx dt. So all I got to do is I'm going to come back here, and I'm going to say, well, whoa, we want to know precisely when he's 10 feet. Well, there's nowhere for me to plug the 10 feet in there, right? So that's okay. So I know 10 dl dt equals 6 times, what was my dx dt? Dx dt was, ooh, it wasn't positive 5 feet per second because he's walking towards the pole. That distance is decreasing, so that's going to be negative 5. Okay, so what do I get? I get dl dt. I get dl dt equals negative 30 over 10, which is negative 3 feet per second, which is the length, equals dl dt. That's the length that the shadow is decreasing at that moment in time. Okay, well, that's dl dt. They also wanted me to know, okay, at what rate is the tip of the shadow moving? Well, the tip of the shadow is moving. Well, okay, so now the shadow, how do I find the distance from the light pole to the shadow? Because everything is related to the light pole. So I know my shadow tip, or how do I want to say this? I want to say the tip of the shadow distance. So this is going to be tip of shadow distance equals x plus L, right? So the tip of the shadow, the change in the tip of the shadow, the speed of the shadow is going to be, I don't even know how I'm going to do that. I'm going to call it dt d little t. The change in the tip of the shadow with respect to time is going to be dx dt plus dl dt, which is simply change in the tip with respect to time is going to be, well, I know dx dt. I know dx dt is negative 5 feet per second, plus I know the change in the shadow length is negative 3 feet per second. So I know the tip of the shadow is going to be negative 8 feet per second. And that little bugger's cruising for a bruising. Okay? And that's how I find the speed of the tip of the shadow. Okay? It's all related to where the shadow is to the light post. Okay? And the tip of the shadow is x plus L away from the light post. So the change in the tip equals the change in the walking speed plus the change in the shadow length gives me the speed of the shadow, really. The tip of the shadow, how fast the tip of the shadow is moving at that particular moment in time. Now notice, they never really made me use this anywhere, did they? They never really plugged that 10, or didn't have to plug that 10 in anywhere that I can think of. So that's where we're at. Have a good rest of your day. Tomorrow we start L'Hopital's rule.